Hi everyone, my name is Suriya, and I wanted to talk about our project on tracking P4 program execution in the data plane. Using this idea, we are looking for ways to utilize live traffic to track the behavior of P4 programs, allowing us to find bugs introduced by the P4 compiler. So for a bit of background information, the P4 compiler is in charge of placing all of the resources the input program requires onto the hardware target. Unfortunately, this is not a simple process due to hardware restrictions, and in order to surmount these restrictions, the compiler will oftentimes introduce changes to the program in the name of optimizations. These optimizations can sometimes introduce compiler bugs, such as if-else statements always taking one branch, or incorrect allocation of space for variables. These bugs will disrupt the logic of our code, changing the way the packets are processed. Unfortunately, such compiler bugs are difficult to understand and often require help from a support team. So to get us started, here's an example of a simple P4 program, sourcerouting.p4, taken from the P4 tutorials. On the right is the program's corresponding control flow, representing every possible way the software expects to process a packet. A smart developer will have a picture of this control flow graph in their head while writing code. And as I mentioned, a bug in the compiler occurs when the packet takes a path through this control flow that it was not originally intended to. So we asked ourselves, can we track the way the packets are processed by one P4 program on a switch? Doing this would allow us to follow the behavior of the compiled program in the hardware. So a naive solution to this might be to reserve 1 bit per decision in the program and to flip that corresponding bit if a packet takes that decision. Unfortunately, there are many challenges to face with that approach, specifically in terms of scalability. For instance, the largest program that we have, switch.p4, has about 10 to the 34 different ways to process an individual packet. Yet we are only allotted a limited per packet state to perform any calculations that we may need. So what this means is we can't rely on our naive solution, and we need to develop some sort of efficient method to track our packet execution paths. So to understand why packets may take the wrong path, we have to delve a little bit into the piece of hardware. So in the hardware, programs are essentially just a series of match action units acting on a packet, and these match action units are all placed on successive stages, creating the P4 pipeline. Remember, this is done by the compiler and is a bit of a messy process because honestly, the compiler has a really difficult job to do here. The P4 pipeline is very streamlined for fast packet processing, and actions happen concurrently within the stage. Yet, the compiler must make sure to create no race conditions such as read-write conflicts due to actions attempting to access the same resources concurrently, such as within the same stage. Thus, it's only natural for the order that actions appear in the control flow to not be the order that they actually appear in the pipeline. And for visualization of this, we may end up with a crazy scenario looking like this, where there is no intuitive human ordering. So an observation that we did have, though, is that because of the linear nature of the hardware pipeline, no program's control flow path can be cyclic. Thus, every program's control flow graph can be represented by a directed acyclic graph, commonly referred to as a DAG. Lucky for us, there is a relatively straightforward algorithm that will compactly identify the path taken in a DAG. This is the Bolaris algorithm. For the scope of this talk, it's important to know that the Bolaris algorithm calls for an update to a single variable on edge transitions, and with it in place, each path through a DAG will be uniquely identified by the sum of the edges that that path traverses. So let's look at what this looks like for our example program. Now we have the variable v, which represents our path variable, and we see green boxes on edges representing the amount to increment the variable v. The final value of v uniquely identifies the path that was taken. So for instance, let's trace this path, A, B, D, E, F, H. So from the top, A, B, D, E, F, and H. What you'll notice is that this path sums the variable for v to 2, and this is the only path that does this. So with this methodology in mind, our overall system is going to look a bit like this. Given an input program, we perform Bolaris encoding, giving us an encoded version of the exact same program, and we choose to run this encoded version in the hardware target instead. Unfortunately, we can't simply implement Bolaris due to a couple of restrictions. So we've already talked about how programs potentially having a huge number of paths, which would make a single variable arithmetic not scale. In addition, updating just a single variable will create extra dependencies between actions, and these extra dependencies may change the way that the compiler performs its original hardware mapping. And this is something that we really want to avoid, as it essentially changes the system that we are attempting to track. So we ensure that this doesn't happen by verifying that every action in our original program maps to the exact same stage in our encoded program. So returning to our control flow for our example program, let's further analyze it to understand why a single path variable may be insufficient. Let's say that actions C and F are both on the same stage in the hardware pipeline. What this means is that they cannot both update the same variable V at the same time, as they would then experience a race condition. So an idea to get around this might be to have these actions update different variables rather than both of them updating just V. So an idea that we had to get around these restrictions is to partition our input graph and run the Bolaris algorithm individually on each partition. So what this looks like is we may end up with one partition like this, which includes the action C. Notice how now we're performing an update to a variable v1, and the update between B and C is smaller than it was before. Our other partition would then look like this, and it includes the action F. And as you'll see, this partition completely ignores v1 and would only perform updates to v2. As a result of these partitions, you would need both the variables v1 and v2 together to identify the path, rather than just our single variable v. So to get into a little bit more detail about our multivariable solution, the idea is to essentially partition the control flow graph to run multiple instances of Bolaris at once. Mutually exclusive actions can be placed in the same partition, such as actions from the same table or actions on different stages, because these are not ever in a case where they could form race conditions. So we assign Bolaris variables to every partition for performing path updates, and we will run the Bolaris algorithm on each variable subdag separately. Afterwards, our path will be uniquely identified by the tuple of our Bolaris variables. So keeping that in mind, we will need to minimize the space that our tuple of Bolaris variables requires. This is a very important step to ensure scalability. Otherwise, we could still end up with our naive solution of a 1-bit variable for every decision if we over-partition our graph. So without getting into too much detail, we make sure we minimize our hardware overhead by solving a linear program that decides which actions update which variables, and the constraints of the linear program ensure that the tables do not form any new invalid dependencies and that the overall size of our tracking bits is minimized. So we tested our system for Tofino hardware target with 6 different input programs of different levels of complexity. The right half of the table shows the number of variables that we need to track all the paths in the program, as well as the size of that space. We're most interested in scalability by showing our approach works for even the largest programs with the least state available for use. So why don't we focus on just those data points? So for our 3 most complex tested programs, the second to last column represents how many bits our approach required, while the right column is how many an optimal single variable solution would require, which is the minimum number of bits required to store all of that path information, simply log n. In all cases, what we witnessed is that the introduction of our metadata worked smoothly, and our encoded programs compiled for Tofino, and packets at the end of the pipeline would be tagged with the path that they took. Even for the most complex program, the amount of bits that we needed, 178, was only marginally greater than the optimal value for the unfeasible single variable Bolaris algorithm, which is 114. More importantly, all of our encoded programs do not use all of the bits that we have available. So in conclusion, we have motivated the need for a data plane primitive to track packets' execution paths and have adapted an existing algorithm to give us our multivariable Bolaris encoding approach, which we have implemented on Tofino. Our future work for this project is to use the paths that we see in live traffic in real time to detect and localize any bugs that may have been introduced by the P4 compiler. Thank you. Feel free to contact me if you have any questions.